My favorite page.
Yeah, okay. I was going to ask.
Not my favorite page.
Oh.
High round. I think you'll tell us how to get experimentalists interested without waiting 20 years.
Yeah, this one happens. Anyway. Okay, so yesterday, I think a lot of question was raised. First of all, is there any question for the last lectures? Okay. There were questions raised about what's the difference between equilibrium and non-equilibrium system, and so on and so forth. I think this is very much leads to this lecture. And also answer the questions, where have I been? So, okay, this is my last lecture, so I'm leaving tomorrow morning. So I'd like to thank the organizer and particular Peter so pestering me to come, which I'm so happy I did. I was not totally convinced because the subject is active matter and in particular flocking theory, which I did with John Toner 28 years ago, right? So before most of you were born. So I was a little hesitant to tell you something that is so ancient. But I'm glad I did because every time I look back, I think it through, I gain something new and I sort of start thinking about it again. Okay, so going back to where I have been. So since 98 and early 2000, I sort of slowly moved into biology, but always with the root that is non-equilibrium physics. Because I firmly believe I'm interested in non-equilibrium physics, but where to look for non-equilibrium physics of non-equilibrium system, there's no better place than living system, right? So anyway, but before I go there, this is actually related to the question people ask about what is the difference between equilibrium system and non-equilibrium system. So I put down here Peter's favorite paper. I don't know how many people has read this paper. Well, okay. Less than RG, but bigger than 0, bigger than 1. That's pretty cool. Why I put this paper on here? Because this paper basically, okay, if you think about equilibrium physics, if you just want to understand the steady state behavior, you don't need dynamics, right? Write down the partition function, given a Hamiltonian, you're done, right? But if you really want to understand the dynamics, how it actually reach there, and what is the fluctuation, dynamics of the fluctuation, and how they propagate, and so on, then you need to write down the dynamics for that equilibrium system. So what is the dynamics for a equilibrium system, right? So this paper basically tells you all different kinds of dynamics correspond to different systems that they classify using model A to J. Actually, I'm not kidding, right? It's actually really, I couldn't find model D very carefully. I think D and E are sort of similar, so they, yeah, anyway. Based on the following. So this is also the classification scheme also says a lot about what I told you before in the first lecture, which is how do you construct hydrodynamic theory? You construct based on whether the order parameter is conserved or not, right? Conservation law. Whether there are other conserved properties like density, number of particles, right? In this case, in the flocking case, whether there existing coupling between these modes. Of course they do. The density actually is coupled with velocity. So basically you can classify this model based on the symmetry, conservation law, and so on and so forth. And they did that, and they have model A to J. So if you are interested in how to construct hydrodynamic theory for something, this is a very good reference to look into, because it tells you everything about how to construct it, how do you solve it, how do you using RG to solve it, and look at it's focused on critical phenomena, but doesn't have to be. So it's just the general ideas are out there. Okay, so why I'm telling you this? For obvious reason, I want to use this as a backdrop for saying what is different between equilibrium and non-equilibrium hydrodynamics. Equilibrium hydrodynamics, deterministic part can always be written in some form as a gradient descent. What are you descending down? You're descending down the free energy, some global function, right? And the noise has no feature. It's white. Its strength is connected with the what we call the kappa. The kappa appears. Kappa is like a coefficient, right? How fast you decay down. Kinetic constant. How fast you decay down the gradient. You descend down the gradient, and that appears also in the noise with a factor delta. So why is this equation special? This question is special because you actually can solve it. You solve the steady state distribution. You solve it by solving the Fokker-Planck equation. And the steady state of the Fokker-Planck equation tells you the steady state distribution of the field. And it follows the Boltzmann distribution. You can try it. Maybe field is harder. Try one single variable or multivariable. Basically, you get back to the Boltzmann distribution with delta. Remember what's delta? Delta is the ratio between the noise strength and the kinetic coefficient. And that's your temperature. That's your KBT. But that's the Boltzmann distribution, right? For example, people have constructed what people call the 5-4 theory for XY model, equilibrium XY model with the long wavelengths in hydrodynamic limit. You actually can describe it by the following equation, the blue equation, dynamic equation down there. Maybe you can push down the middle one as well. I can point there. Okay. I don't want to be biased to the left or to the right. I can jump. Anyway, so this dynamic equation is obtained by saying, okay, for the XY model, you have at long wavelengths and long time scale, well, time scale is not involved here. It can be described by this coarse-grained free energy functional, right? It's a functional because it depends, it's a space, it's a field, right? V is a field, and depends on the gradient squared. And this is a familiar term that we use in our model, right? In the TT model, right? So if you plug that into here, this is what you get. Well, K kappa equal 1 here, okay? So you get this equation. This is the equilibrium dynamic equation for the XY model. Now, let's take a look at our equation. It cannot be written as a total derivative term plus a noise, right? Or any other form, because it's not conserved. So I shouldn't add a grad square here, it's just this term. So I challenge you to, counter me. Try to find F that actually this equation is satisfied with the form of F. You can, but challenge me. I think you can. We couldn't. Okay. So where did that lead us? Where does this connect to my story here, the first part of my story? The story is, okay, now I have told you that the system is not out of equilibrium. So what? Who cares? It tells you one thing that's very, very important. If the system is out of equilibrium, in the fact that, well, I'll tell you later that beta balance is broken and all that stuff, then even in the steady state, it can still reach a steady state, right? Dynamic equation reaches steady state. Even in that final steady state, to maintain that final steady state, there has to be continuous dissipation of energy to maintain that steady state. So there's a cost. There's a continuous cost to maintain that steady state. Nothing's changing with time. Seemingly useless, right? But it's actually tell you. So the question that we have been asking ourselves for the last 15, 16 years is in various biological systems, what is the cost? Here's the cost, energy cost, and performance. Of course, in biological systems, you don't just burn those ATP for nothing, right? Obviously, your biological circuit is trying to do something. And the performance of that particular function that you're interested in, what is the cost performance trade-off? Is it more energy dissipation the better? Or, otherwise, how does it relate to the characterization of the function? The function is a very fuzzy, it become more clear later for a particular example. So this is what I've been working on in various systems. One of the things I've been working on. And so I'll tell you one story along those lines. Then after that, I'll go back to flocking. Okay. All right, so this is lecture 3. So really the title is Energetics of Collective Phenomena in Strongly Interacting. I like the word strongly interacting, it's borrowed from condensed matter physics. It's really individuals are strongly interacting with each other. And that's how the collective behavior evolved. So what we're trying to do is trying to understand this interaction between individuals, whether that leads to an energy cost. And how would that energy cost lead to the connect with the collective behavior that you're interested in? Yes. Non-equilibrium steady state is that if you're interested in the probability distribution of the system, it reaches steady state, right? That means if you look at so think about the Fokker-Planck equation, right? And you solve the steady state of Fokker-Planck equation. And when the time scale is longer than relaxation time, you reach a steady state. And that steady state can be a non-equilibrium steady state, or it could be an equilibrium steady state. I'll show you how do you distinguish those. So for the biological clock, first part, these are the people who did work, my collaborator did the work with me. And for the second part of flocking, is actually a very talented student, currently a Princeton grad, but he did all of this when he was an undergraduate student at PKU. All right, so, okay, let's start big. Let's ask a big question. So how many people read this book? Okay, actually, this is more than helping episodes. It's okay, he's a Nobel Prize winner, okay? So Schrödinger, after quantum mechanics, he was just attention turned into biology, living system. He wrote this book. Many of the ideas and thoughts is very deep at that time, but turned out to be wrong and not so accurate. But there was one thing that cannot be wrong, actually, it turned out to be, right? It says, this is a translation, life feeds on negative entropy. What does it mean is he basically said, look, the system cannot be a closed system because it has to, negative entropy basically means that you see order coming out of the biology. How can you have order? I mean, thermodynamics second law says in an isolated system, the order disappears, right? The order actually appears in biological systems. How could this be? It must mean that it feeds on negative entropy, by which he means life costs free energy, costs energy, right? So he already said that. The question is how and how much? So here are some of the systems that we worked on. So added this on just the last minute. This is most of the things that we worked on before. That basic question is that how do living systems process information and perform its function accurately with very noisy components? One of the general thoughts about all of this, why life costs energy, is that there's a lot of noise in the system, very huge amount of noise, because there's only a small number of molecules exist in a system, in a cell, and much smaller, 1,000, 100, maybe for DNA, a single one, and so much noise, and it operates in room temperature, right? A huge amount of noise. One way to counter that is by designing clever machinery to correct this error, to eliminate those errors. But those mechanisms cost you energy. So that's how, in general, you relate these two. So we have spent a lot of our effort in trying to understand the mechanism, detailed mechanism, how does the machine build up, which component interact with what, and design principles for achieving the biological function, the behavior. So, but today I'm going to tell you about the red part is how much. Okay, now you know how it achieves it. Can you look in detail to say how many fuel, how many ATP that can you burn for you actually to achieve that function that you desire? Okay. So basically, the energy cost for creating and maintaining order in noisy, non-equilibrium system. Okay, let me jump back to physics or chemistry. He won Nobel Prize for chemistry, right? So for actually not for the solving of Ising model in 2 dimensions, but having the reciprocal relation. So this is a Nobel Prize winning paper. How many people read that? Doesn't count? No, well, actually the paper. So if you read the textbook, this is what the textbook would say, tell you, right? So in the equilibrium system, you have the so-called the Anzagar reciprocal relation, meaning that you have all this input, x1, x2, x3, and you have current, that the change in the direction x1, x2, x3, and there's a linear combination of these inputs, right? But so with a linear coefficient, and Anzagar says basically that this response matrix has to be symmetric. He proved it based on a very simple principle. Who knows that? What is the principle? Time reversal solution. Right. So if you operate x1 first and then x2, it's the same as x2. All right. So okay. So why do I tell you this? He further on in section 3, you read carefully. He actually make an analogy to chemical reaction system. You have 3 species, A, B, and C. They react with reaction rate A go to B with a rate KAB, and KBA is the reverse, and so on, right? So some people mention detail balance, very good. So what detail balance tells you is that in steady state, if you're in equilibrium system, in steady state, the flux going from A to B, meaning that the probability in A times the rate from going from, I think it's reversed anyway. So if you are in A and you go from A to B, that's the current going to B, has to be equal to the reverse current. If you are in B and you want to go from B to A, and on each link, you satisfy this condition, right? That's detail balance. But detail balance is useless in the sense that you have to know, if suppose I only give you KAB, all these reaction rates, you have to solve N first in order to tell me whether detail balance is satisfied or not, right? Then he said he has another equation. He said, well, not necessarily. You don't have to do it. Same thing as goes like the scaling law. You don't have to solve the equation to know the answer. He said, well, if you have a cycle like this, and if detail balance is satisfied, then there's a cycle rule. If you make the product of all the rate going in one direction, that product should be equal to the rate going the other direction. Again, this is time reversal symmetry at play, right? So that's the cycle rule. So here comes my other hero. How many people know what Terry Hill is? 0. All right, he's a chemist, but he wrote a lot of textbook on thermodynamics. And so this is like actually the favorite book, Free Energy Transduction and Biochemical Cycle Kinetics. So what Terry Hill did was really focus on non-equilibrium system. He didn't call it that way, but non-equilibrium system, chemical system, because he's interested in biochemical network, right? So he basically used the same reaction as Anzagar wrote in his paper. Basically, you have A, B, C, and C. If the cycle rule is broken, then you know detail balance is broken, right? So then so what? Then further on, what his contribution is that then he said, well, then there's a persistent current, even in steady state. Even in steady state, there's a persistent current going around the cycle. And that persistent current will cost you. And how much does it cost you? It costs you the free energy dissipation rate W dot is J, the current, times the chemical potential difference, the thermodynamic, what he called the thermodynamic force, right? So you say, well, okay, if you look at this equation, you know, it's harmless, but something, if you look carefully, then this actually turns out to be always a positive definite number. And it's only 0 when detail balance is satisfied. In other words, dissipation rate is 0 only when the system is in equilibrium. In equilibrium, if you're in a steady state, equilibrium steady state, it doesn't cost you anything. You are reached equilibrium with a thermal bath, right? There's nothing externally driving you. Whereas if you're out of equilibrium, as long as it's not equal to 0, this is a positive definite number. That's the dissipation rate. And some people call it the entropy production rate. And if you times KBT, that becomes a free energy dissipation. Okay, that's what we're going to use interchangeably energy production, free energy dissipation rate and entropy production rate. Okay, all right. So that's that. If you remember something from this talk about the general non-equilibrium versus equilibrium, this is something you should remember. In the context of reaction network, which I think transition state in the state space, everything can be considered as transition matrix and so on. So that's the basic. And furthermore, if you have a bigger network, consists of more than just the 3 nodes, it says that in equilibrium system, any cycle rule has to be obeyed. In other words, if you have a larger network, if any one of them detail balance is broken, that this cycle rule is not satisfied, the whole system is out of equilibrium. All right, so this is what we have been using this to calculate dissipation and connect to various biological functions, right? In this case, we studied the switch, how sensitivity of a biological switch depend on the energy cost. We studied adaptation, how accuracy and speed of adaptation depends on energy cost. We studied biological oscillatory system. And today I'm going to tell you about synchronization of individual molecular clocks and how they synchronize and how much does it cost you to synchronize. And we have written some general theory about inverse Hall law of dissipation rate during post-graining and so on. So that we won't have time to tell you anything about it, but this is a line of thinking that we're going down, right? Starting with in early 2000 and later. Today, I'm going to tell you something a little bit more than what we have done before, more recently. So what we've done before has been always within sort of a chemical reaction network, but it's well stirred, right? In other words, there's only concentration, but there's no spatial or individual agent-to-agent variation. Right? Well stirred reaction. Today I'm going to tell you 2 examples. One is synchronization of molecular clocks. Another one is actually really fresh out of the oven, submitted last month, clocking of active spin. So it's very subject-wise appropriate to this talk. Okay, so what is a clock? What is the simplest minimum model of a biochemical clock? It's really a clock. These are ticks on the clock. You have what, 12 ticks on the clock. And from but this corresponds to each chemical state. A chemical state will jump to the next state, and there's a reverse reaction also, right? So basically, you want the reverse reaction to be smaller. The little gamma is a small value. And so on. We just have this sort of a global clock cycle of clock, individual clock. So we consider coupled clocks. There are many of them, right? So if you only have one such clock, you can check yourself. This is a lousy clock. It doesn't do very well because it's a profound process. Depending on how many intermediate states you have, the noise is huge. But what if you have multiple clocks? And this is really happened in biology, that there's actually in each individual molecular clock, it's just one, let's say, hexamer of some molecule, and you have tens of thousands of them floating around, interacting with each other. So if you think about 2 clocks interacting with each other, and the phase of each clock is one coordinate, and this 2 coupled clock lives on a torus. Right? And besides the clockwise, so each motion around for individual clock corresponds to the motion around either this direction or this direction, right? The interaction happens when you introduce this red interaction. That corresponds to 2 clock exchange phase, right? One move a little slower and one move a little faster. One increase their phase by delta phi, another one decrease by delta. Okay. So it's like a spin-spin interaction. And the interaction called exchange interaction is basically characterized by the exchange rate. Remember, this is the one chemical state, go to another chemical state, you have a rate, and you have an inverse rate. This is the forward rate, this is the backward rate, and the ratio is basically e to the delta Eij. Eij is the energy difference between the two phases. Seems like an equivalent model. Okay, so that's just basically so you can couple all of them together, all-to-all coupling or just pairwise coupling on a lattice. Right now we consider all-to-all coupling. Yes. Yeah, maybe I like that. I didn't think about it that way, but I like that. Yeah. So I like that because, well, it has to be a periodic function, of course, but it has to depend on the difference because I want them to be close. Basically, this interaction, the effect of that is that if I'm talking to you, I know your face, and I know my face. Our face is getting closer, right? So this is ordering. This is alignment. This is alignment term. Right? But each clock is moving its own speed. So so each clock here can go this way. So this is a clock I. It can go only horizontally, or it can exchange phase with another clock by change. So it has two ways to do it. Okay. So why I'm telling you all the detail. So remember the cycle rule. So this all now each grid point here is a state, chemical state. What I'm going to tell you is that there are two types of cycles, reaction cycles, exist in the system. One, global clock cycle. Forget about the other clock. Just go around the phase 2 pi, one cycle. And if you look at the ratio of the counterclockwise versus the clockwise rate, you get gamma to the n, right? Now gamma is less than 1, so this is not equal to 1. So this costs you energy. To run this individual clock runs individual clock costs you energy, right? Because of this. Now, because the coupling, you have another local loop here, right? Of course, you also have this bigger loop, but that loop is equilibrium loop. That gamma is 1. But because of this coupling, you have this little loop. You look at the gamma, the ratio for this little loop, local loop, you find it's e to the minus delta Eij. So as long as your phase is different, this will cost you energy. That already tells you that synchronization costs you energy. Right? So that's the final punchline. The exchange interaction is characterized by the frequency of interaction. So you imagine many clocks floating around, and occasionally they hit each other and they interact. So this omega is the frequency of interaction, how often they exchange. E0 is how strong they interact, which is how strong they align, right? Okay. Actually, turns out this, yes. Oh yeah, it is. Yeah. That's detail. Yeah, the phase coupling exactly is Kuromoto model. Yeah. Yeah. Actually, Kuromoto model, they worry about something different. They worry about if you have intrinsic frequency determined by the K, which is different from clock to clock, can you actually synchronize them by using this coupling, right? I'm talking about if each individual clock is very noisy, but the intrinsic frequency is the same, but they have huge noise, can they synchronize? But I'm not asking about synchronization per se. I know they will synchronize based on Kuromoto. But I'm asking, how much does it cost to actually synchronize? Right? So that's the question. Okay, so this model can be solved actually exactly. I think it's only in this limit of K being constant instead of varying from clock to clock, you can solve it. I think we solve it analytically. Basically, you have you actually end up with a distribution function, which very much look like the Boltzmann distribution, but instead of beta being the normal temperature, which is 1, we set to 1, the interaction delta E divided by 1 is actually 1 plus K over omega. You already know this is a non-equilibrium model because it depends on the frequency of how often you interact. Okay, so in the equilibrium system, another lesson. In the equilibrium system, the final steady state distribution should never depends on rate. Time is out of in the final distribution. If you see anywhere a final distribution depends on some rate, you know the system is out of equilibrium. Okay, so this is a phase diagram probably very familiar to people. So if you plot the asynchronous phase versus the synchronous phase in the parameter space spanned by the frequency of interaction, exchange interaction, and the strength of the interaction. And you see the more often you interact and the stronger you interact, you allow the system to synchronize. The order parameter is basically the sum of all the phases. Each side is a normal order parameter. Because we can solve the problem exactly, we actually know exactly the critical line. And this is it, right? So this is order, disorder. This is actually a non-equilibrium phase transition, if you wish, from an asynchronous phase to synchronous. But we're not interested in the transition per se. We're interested if I'm here, how much does it cost? If I'm here, how much does it cost? So would you guess if I'm here, I don't cost you anything? No, as long as you're out of equilibrium, which this point is out of equilibrium, will cost you something, but not enough to push you here. So we actually not only can compute the dissipation rate, we actually can decompose it into the processing energy, which each clock process around takes energy. So this is the part that per clock costs you, processing and exchange energy cost. Because basically gamma G and gamma L. And we compute, let's focus on this part. Per clock energy cost is a base cost, which doesn't depend on the interaction. So we're focusing on the exchange energy, plotting that in the omega versus E0, right? So even here is not 0, but it increases, right? And across this is a phase function here. Plotting the different coordinates, log scale. So you actually can compute the exchange energy for any combination of E0 and omega. Right? So let's plot it along this line. Oh, along this line, sorry, along this line. If you fix E0 and the changing omega, change the frequency, right? And instead of plotting it versus omega, we plot the cost versus the order parameter. Or the order parameter versus the cost. This is what you get. This is exchange energy cost. This is the order parameter. So you see that this figure shows you that not only you need to cost you energy, but you need to cost you a finite amount of energy to create the order. There's a critical point here, corresponds to the amount of energy cost. But that energy cost depends on what your strength of interaction, right? The stronger your interaction here, the more it costs you to actually at the onset of synchronization. So then you have an issue of, then you can think about an issue of design, right? Suppose I have, what is the envelope looks like, right? This is the best performance. This is the least amount of, for given values, this is the least amount of energy cost to achieve the maximum of, for given amount of energy cost, the maximum synchronization you can ever achieve. That's the envelope. And the envelope follows some. And at the envelope point corresponds to this envelope point corresponds to a particular choice relation between E0 and omega, which is like I draw here, which I call the optimum design line. Suppose you can design your system by changing E0 and omega, and you want the the same performance for minimum amount of energy cost. And that's your design line. Okay, so back to biology. But does it really happen? How many people know about the Chi system? One? Better. I feel bad for. Anyway, so the Chi system is probably the most fascinating biological molecular clock there is in nature. Right? Why do I say that? Well, it happens in this Synechococcus elongatus. It's a bacteria cell. I think this is about micron. So sort of several micron long. This is the only bacteria that actually have 24-hour rhythm. It has a 24-hour rhythm. It has a circadian rhythm. Right? This is cyanobacteria. It needs it to so basically this is actually the very important bacteria because it's the first line of business of harvesting energy from the sun. Okay, so therefore it needs the 24-hour for obvious reason because the sun goes up and down in 24-hour rhythm. It's also fascinating. So you can look at the expression of all the different genes that actually oscillate. This is 24 hours, right? So it doesn't really have a very strong 24-hour rhythm, right? So why I think it's so fascinating? It's fascinating because it's revealed to us in 2005 by this Japanese group that he actually was able to reconstitute this clock in a test tube by using only 3 molecules, 3 proteins, Chi A, Chi B, and Chi C. I think Chi in Japanese means time or something. Any Japanese? Does that mean, does Chi mean anything? Anyway, so basically, he basically extract this protein, purify this protein, and put it in the test tube with some proportion, and it oscillates. I missed one thing. What did I miss? Add ATP. So if you just have 3 protein in there, remember the movie I showed you on the first day? If you don't put ATP in that microtubule and kinesin soup, nothing happens. So once you add ATP and all these 3 components, 3 protein in, start oscillating 24 hours. So what is the key component of this clock is a hexamer. This is a protein Chi C, consists of 6 monomers formed in a ring of hexamer. And this is an amazing clock because it also has 12 ticks, just like our clock. And what is each tick? Each of the monomer has 2 residues that can be phosphorylated. So 2 times 6, 12. Right? So basically, at 6 a.m. correspond to you have 6 of the TP, the P residue, sorry, at the T residue being phosphorylated. At 12 noon, both the T residue and the S residue on all the hex monomers are phosphorylated. And at 6 p.m., only 6 of the S residue remain phosphorylated. The 6 T are gone. And back to 12 a.m., everything's gone, not phosphorylated. So 24-hour cycle. How do individual Chi C hexamers synchronize? So there are studies and models to tell us how each individual hexamer works as a clock, and it does. Nobody measures it, but it seems to be true that each individual clock can oscillate. But if you imagine what they measure, this oscillation, when they measure this, they did not measure individual molecule, individual hexamer. They measure thousands, tens of thousands in the test tube, maybe more. So that means not only they have to oscillate, they have to synchronize in phase. Otherwise, if the phase are random, all you're gonna see is just a flat line. Right? Make sense? Yes. Yeah. Oh, rotation. Okay, can you write the word chi-10, T-E-N? Oh, chi-10 means rotation. Cool. Always learn something new. Thank you, thank you. Yeah, I always assume, yeah. So you say what? Life? Oh no, this is all in the totally constant light situation. If you have light, you can entrain. If you have a periodic light, like light, you can entrain the oscillation. The phase degree of freedom is actually very flexible, but they are synchronized. So there's a separate study about entrainment. All the experiments are done in a constant temperature. Notice no other time scale imposed, no constant light, and they oscillate. So this is really spontaneous, symmetric, whatever. Yeah, this is spontaneous oscillation. Yes. Molecule level, I wish I could tell you, no. People have done, well, we can estimate it because people have done individual step of the reaction. So there are other two elements, Ka, Kb involved. So individual biochemical reaction rate has been measured. So judging from that, you can probably tell, because it's a single molecule problem, judging from, given the reaction rate, you can probably estimate the noise, which is going to be just tremendous, right? Because this is really a single molecule. The single molecule Poisson process, the noise is just incredible. All right. Okay, so I'm already spending, but this is fun, right? I rather spend more time talking about this. So, okay, so I told you about a mechanism, theoretically, how you actually can make the two systems, make individual clock talk to each other, exchange phase, and then become synchronized. Told you that, right? Depending on interaction strengths and frequency. How does actually chi-C hexamer synchronize with each other? How do they exchange phase? This is such an amazing experiment, I have to tell you. Again, from the Kondo group, they did the following experiment. They suspected, I don't know why, that these hexamers are not just running solo. They actually bump into each other, and not only bump into each other, they exchange monomers. So what they did is, by clever biochemistry, they label, they have two test tubes. They label in one test tube all the monomer by some marker, right? So these are guys with little thing attached to it. Another test tube, nothing, right? And then they mix them and measure it later time. What they find is that all of the hexamer now have this little tag. What does it mean? It means that they exchange partners. They exchange monomers. It's called monomer shunt. So what does monomer shunt tell us? Remember, each monomer carries a phase, right? Because phosphorylation level is reside on the monomer, and that's the phase of your clock. And if you change partner, you exchange your phase. There's a related puzzle, right? So this Kondo group is just great. I mean, doing all this very meticulous, but very, honestly, like even physicist style experiment, right? So basically what they did the following. They actually measured how many ATP is being used for each clock cycle, for each monomer. Remember I told you that each monomer during a 24-hour cycle get phosphorylated and then dephosphorylated twice. So people who know about biochemistry know that phosphorylation, for phosphorylation to happen, the donor is the ATP. In other words, twice a day, a monomer will cost 2 ATP to run the individual cycle, right? Phosphorylated, dephosphorylated, phosphorylated, dephosphorylated. And there are 6 of them, right? So now, So seemingly for that single clock to work, only 2 ATP is needed. But when they measure in the test tube how many ATP has been consumed, they find 16 ATP are hydrolyzed per Chi-C cycle per day. So that's a big gap, right? The question is, where did all the other 14 ATP gone? It went, right? So the best guess is, our guess, of course, we think it's used for synchronization. So we built a model which built into the fact that they actually do monomer shuffling. They also do an individual cycle that's going through all the detailed biochemical steps, going through conformational change, phosphorylation, dephosphorylation, and this is an individual clock cycle for individual hexamer. And then you allow monomer shuffling at certain phase of your clock. And we basically study that model and we allow this to happen with some frequency R, and we control the R, frequency of exchange. And we find that indeed, in order for this model to have a synchronization, this is actually a synchronization order parameter, you need to have finite frequency of exchange. So you have no exchange, of course, it's out of synchrony. So you have to have frequently enough. Come with that is additional cost. So this gray bar is the baseline, 2 ATP, right? This is with different interaction strengths. Remember E0 or E0. For different interaction strengths, your dissipation rate will go up with R, right? This is the 16 ATP per day. So with the estimate of interaction strength, this is in some units, so I don't want to go to much detail. That it actually, this is the additional cost beyond individual clock cost for synchronization. And you see this additional cost actually bigger than 2 ATP, and it's closer, maybe not quite as. So I think we believe that's actually really the mechanism really is synchronization actually costs energy, and the observed discrepancy between the 2 ATP and the 16 ATP measured, probably most of it or some of it, big fraction of it is used for synchronization to drive the and finally, I think we also have a candidate of where that energy is being used. So this is the structure of the Chi-C hexamer. It actually, instead of having one, so I talked about C2 ring, which is the top ring, C2, which actually have 6 monomers, each monomer have a C2 domain, and the phosphorylation resides here, only on C2 domain. But it's also underneath it, it's another C1 domain for each monomer. And that's where ATPase is. How many people know about what ATPase is? Okay. ATPase is basically a general name to use for ATP hydrolysis. It's a machinery that do ATP hydrolysis. So your motor actually is an ATP hydrolysis. It's ATPase. People know it's ATPase. So most energy probably was burned here, but people did not know what it's used for. Now we have a very good hypothesis. This is probably useful, not just wasting it, but probably used for synchronization by, for example, blowing it up. But how do you exchange? You have to disassemble it, right? Disassemble it and then reassemble. Okay. All right. So now we're going to switch gear back to blocking. Any questions? So this is actually quite different. But it's still a collective behavior, right? It's a collective behavior between clock, time changing machines. Yes. Not the precision, just the amplitude. That's just the main. Without synchronization, your average behavior would not have any amplitude at all. Would just be flat. Would not have any oscillation. Say again. Yeah. Yes, absolutely. Yeah. If you think, I think the absolute measure of performance, this doesn't change the frequency. what it changes is increase the amplitude, because the synchronization amplitude of the collective, basically it's like the V0 in the flocking bird, right? So every bird is moving, but if they're moving the same direction, then you have or correlated, then you have a finite V0 average over all the birds. But if they are, even though each one of them is moving with a constant speed, they're moving in different direction, not synchronized or not aligned, then you got on average you got no collective motion. Yeah. Professor who? I don't know him. Okay. Yeah, sorry. I just, I know. Yeah, no, but I'm saying something quite trivial here. No, I'm saying all non-equilibrium systems cost energy. Living systems are out of equilibrium. If you're not out of equilibrium, you're dead, right? So therefore, there's a cost for life. That's actually the trivial statement made not by me, but by Schrödinger, right? So I'm willing to go one step further. Is that okay? You cost this much. I know you cost energy. How can I relate the cost with actually the function? So here the function is synchronization, or in other words, the collective behavior, the average, the clock, amplitude. So I want to be very specific. I don't want to make any large statement. I want to study each individual well-defined system and see how the performance, y-axis versus cost. How does it look like? Yeah. Hello? Oh.
Some noise, I think that might.
Oh, so it's not tripping anymore. It's my shirt. Oh, this will stabilize things. Oh, this one. Oh, that's too much to ask. Or maybe I can take off my shirt and nah. So what should I do? Hold on a second. Let me do this. Let's pin it between two buttons. Is it better? Oh, okay. But this doesn't. Okay. All right. Okay. All right. Okay. So let's go back to flocking. Okay. What about flocking? So okay. So we want to study flocking energy cost. I want to study it for a long time. We originally want to study using the hydrodynamic equation that we developed, of course. But it turns out we also did the other study. 2001, we did a study about the constraining and its effect on dissipation. If you compute dissipation at ever more and more constrained level, what we found is quite interesting. Is a sort of inverse cascade. If you calculate at the microscopic scale dissipation, use the entropy production rate, you find that's the true value, right? That's the microscope, how many ATP you'll burn. But if you constrain your model to a larger scale, and you compute the dissipation following the prescription, so to speak, and you find the dissipation rate, the apparent dissipation rate is actually lower. And not only is lower in a large class of system, it goes down as a power law. It's also very, very, very intuitive because when you're integrating out the degree of freedom, those degrees of freedom carries energy. Especially in non-equilibrium systems, the degree of freedom that you integrate out actually carries energy dissipation. So that's where the red arrow is supposed to be. So this is very different from your turbulence case where there's inertial range. Within the whole range, there's no dissipation. Dissipation only happens here. Right? Okay, so to determine the true dissipation rate, we need to compute it at the microscopic level. So VCheck model is a microscopic level model, but that's actually off lattice, and the orientation is have many degrees of freedom. So we can really do it very conveniently. So we need another model. Yeah. Yeah. No, so by apparent, I mean computed based on the observed rate. For example, I give you a very specific example. So this actually the study was not coming from theoretical point of view, it was actually a real experiment. What people did is basically they have developed very sensitive colorimetry. They actually can look at one of these kinesin myotubular soup. They measure actually exactly the dissipation, the heat dissipation. So they actually measured it from here, at this level. But then they look at the large scale flow developed, I showed you in the movie, right? And they look at the viscosity, and they look at the flow rate, the speed and the density and all that good stuff, and they estimate there. That's basically looking at the large scale flow. And the parameter you estimated from large scale flow and use them to compute dissipation, they get 8 orders of magnitude smaller. So that's prompted us to do this study. So actually it turned out to be, people know that cross graining actually, the apparent, loss of entropy production rate is lower because you lost information. All right. So we need a smaller, even simpler model than VCheck. So there comes the model by Tullier and Saloom. They proposed in 2013. This is called the active Ising model. It's a very cute model. So just look at the 1D, right? So basically you have different sites, and you have number of particles n. Each site you can have, each particle can be either spin up or spin down. It's the Ising model, right? Spin up or spin down. But they're not mutually exclusive. You can have as many particles in one side as you want, based on the dynamics. What is the dynamics? Dynamics is that you have two types of dynamics. If you're spinning up, you basically do random walk, right? But if you're spinning up, you have a higher probability to go to the right than go to the left. So your probability of going to the right is d times 1 plus epsilon. Epsilon is the bias that is dependent on the spin. If you're negative, you bias the opposite direction, right? Then you go more often to the left with the same bias epsilon. Okay, that's the motion part, right? Remember, we need motion and we need alignment. So what is the alignment part? Alignment part is that with frequency gamma, I think I put gamma here, it should be omega here. With the frequency gamma, you also have alignment. Basically, depending on, but alignment happens on the same site, right? So you look around your other spin, if majority is pointing up, so basically you have a probability of pointing up depending on the average spin on that particular site. Okay, simple enough. You can play the game yourself. So you have two control parameters, epsilon, right? And the coupling strength. I think coupling strength is demonstrated by beta here, which is, I think I will use later on as E0, I think, the change of notation. So this basically explains what I just told you. The two types of motion, right? One is actually changing to a neighboring side with a bias epsilon that depends on whether you are spin up, bias to the left, spin down, bias to the right, okay? And once you're on a particular side, you have a certain frequency of align with your not neighbor, with people with spin on your same side. And that's it. So there's a relative frequency between motion and alignment. There's a strength of alignment, and there's a bias. That's a 3 parameter, right? So you change the 3 parameter, you run your computer simulation, and you see this phase diagram. So this phase diagram basically tells you if the bias, so gas phase is basically the disordered phase, and liquid phase is the ordered phase. I'll show you a movie. And if the bias is stronger and E0 is stronger, you're more likely to go to liquid phase. This is a movie. So the gas phase is basically, see the M, the blue line is the M, the average spin on each side is roughly 0, right? And the red line is the average speed or average spin on each side. Oh, sorry, no, not actually. Average is that speed? Oh, sorry, density, sorry, what I'm talking about, the density, right? Which is also comes. So on liquid phase is basically, the density again is constant, and the rho is constant, and M is actually bigger than 0, finite, right? That's the moving state. And there's an interesting mixed state in between, which is basically you have a band of moving clocks in the background of not moving, right? But it's not a solid moving front. That it keeps grabbing things from the front, keep losing things at the back. There's a dynamic balance. As a result, it just have a constant width of the band. Okay, so that's one thing I want to demonstrate to you is that, remember, I told you that at microscopic level, the best way to detect whether the system is out of equilibrium or not is detail balance. But detail balance is very hard unless you solve the problem, the probability distribution has to be solved. But the easiest way is actually look at the cycle rule, right? So if you have from one state, you go from one pass and coming back to another pass, and you look at the rate, transition rate along the, let's say, one pass versus the reverse pass, the product, if they're not equal to 1, you know the system is not equilibrium. So I'm going to demonstrate to you with this little diagram that the AIM model, the active Ising model, is indeed out of equilibrium based on detail balance, breaking up detail balance. So here it goes. So the states are separated by bar. So this is in a two-side model, right? You have only 2 sides, right? You have 2 sides and 2 particles, 2 spin. The first state is when both spins are up and sitting on the same side, side 1. And then it moves to the second state, which is that it changes spin. This spin changes from plus to minus. And the rate we can calculate is 2 to the e to the minus beta, right? So it's the blue thing, this way. And then the next move is to say, well, okay, now I want to move this state to this state by hopping, right? So this -1 hop to the next side, 2. What is that? Because this is biased against it. So the negative spin goes biased towards the left. So this transition rate is d times 1 minus epsilon, right? And at this state, I decided to go to the next state by flipping, right? To go on. And then I come back. That's one path, right? One path from the original state to itself. Let's go back to a different path, right? So this guy, I choose one of them. I jump it to the other side without flipping. So that's 2d 1 plus epsilon. And then I change the spin here. That's e to the minus beta. Then I move from 2 to 1, from side 2, the negative spin to this one, and so on. So you can make the product going one way. This is formed a loop, and the other way, right? What do you see? You see e to the minus beta, 1 minus epsilon, 1 plus epsilon squared, not equal to 1. So just give you one specific example. There are probably many, many other loops you can construct. Just to convince you that this microscopic rule, it basically comes down to this non-commuting between the 2 operations. Right? As you can see, the fact that it has bias is actually not that important. You can even set epsilon equals 0, just pure diffusion. As long as beta is not 0 simultaneously, it still breaks detail balance. It's basically because the two type of operation, one is motion and other is alignment, it doesn't commute. If doing one first versus doing other first, it doesn't result to the same state. Okay, so the active Diazimizing model, you can compute the dissipation. So you can read all this math, but it's a book, very nice book, written by Politi and Piccolotti, for a pretty comprehensive introduction to stochastic thermodynamics. It tells you how to actually compute, given such a dynamic process, how do you actually compute the dissipation or energy production rate, or entropy production rate, right? So you actually compute that. Follow the prescription, you actually can compute it, which is what we did. And not only we can do that, we can actually, again, break down the cost into two parts, right? One is, again, the key point for flocking is that there's motion and there's alignment, right? So we actually can break down the this energy dissipation rate, the two parts. One is for motion. That's kind of trivial, right? So motion, of course, if you have a biased motion, it costs you energy. Random diffusion doesn't cost you energy, but with any bias, it costs you energy to do bias. So it turns out to be motion is actually log 1 plus epsilon minus 1 divided by 1 minus epsilon. So that's a sort of trivial part of the energy cost. Here's the non-trivial part: is alignment also turned out to be costing you, right? Alignment by itself seems to be equilibrium, but because remember the exchange energy in the synchronization case, exchange energy by itself seems to be equilibrium, but you are driven by the other non-equilibrium part. Remember I said that in the network, any part of the system that actually breaks detail balance, the whole system breaks detail balance, and you end up costing you, even though you're not by itself is equilibrium. So this alignment energy can also compute, and we did compute. And as a result, we have the following diagram, just like in synchronization. So here is its order parameter for flocking. So when epsilon is small, and when E0, the alignment interaction strength is small, you have disordered phase, V equals 0. When you have strong motion and also large enough E0, then you have flocking state, right? This is the interesting part. We also computed the alignment energy cost. Remember, the motion part is actually trivial, just depend on epsilon, and nothing to do with E0. And this part has a lot of interesting feature. And the most interesting feature, if you have not sleeping, is that it's small here. It's also quite small here. Actually seems to peak right at the transition point. This is a surprising part. Okay, so this is nothing but just transition from disordered state to ordered state as you change the dissipation, the same trick we play by looking at energy that's cost for you to become ordered. So not surprisingly, a different value of E0, it costs you a different amount of energy to actually become going into the flocking state. This is the most surprising part. The alignment energy, this is the transition point. So this is the order parameter, the blue line, right? Going from 0 to non-zero. If you look at the dissipation rate for alignment, it peaks at the transition point. Not only it peaks there, it has a cusp. The first derivative is discontinuous. One is increasing and decreasing. Yes? Oh, yeah, so good point. So this is at the transition point between this gas phase and the band. So around here, you have some combination of the two states. Yeah, linear combination of the two states. Yeah. On both sides. So cusp, so I'll show you the simpler. This is linear. This is exponential, but still have a finite slope there, finite negative slope. Yeah, it doesn't come. Yeah, yeah. It's a true cusp. That surprised us a little bit. Would you be surprised? There's no exponent here. It's just the fact that it's maximized there. Not only it's maximized there, actually have a cusp. But cusp is secondary. I think the maximized there is actually quite interesting that It spent a lot of energy fighting this. So at the critical point, I have a lot of fluctuation, right? So basically, you're fighting the fluctuation very hard. I mean, once you're ordered, yeah, pretty much ordered. Once you're in this phase, you're giving up anyway. That's just my, anyway. Okay, so you can see this cost, basically independent of parameter, epsilon equals 0.1, 0.5, they all have this very sharp cast. So what was mentioned there was a little bit of sudden decrease here. That's what you mean, but the mixed state have this sharp drop because the mixed state. But if you go to a parameter space where there's no mixed state, then you get the cusp. All right, so we try to understand it with a reduced model, right? How do you reduce the model? So we reduce it from number of sites be large to actually 2. So going back to the 2-site model that we started with, the demonstration. But the number of particles is arbitrarily large. So in that case, we actually was able to, well, my student, Chi-Wei, was able to solve it analytically because the phase space become much smaller. So you actually can look at the phase space and compress it into the actually 4 variables, right? So basically, on 2 sides, you can say, well, what is the net spin here? What is the net spin here? Total number of spin is conserved. So you have 4 numbers, right? Spin up, spin down on each side, but you have 1 conservation. Number of particle is conserved. So you really have three variable. So in the 3 variable phase space, you actually can solve it. It's still very hard, but he was able to solve it. The master equation with the 3 variable space, right? So it's still 3 variable. So it's whatever n to the cube space, right? So you still have to do some decomposition in that space in order to solve the problem, which he did. So I don't want to go into the details with that. At the end of this, it's actually, once you solve it, actually quite nice, because if you look at the probability distribution of the total spin, m, or average over the 2 sides, and as E0 becomes smaller, this is a small E0, small alignment interaction, this is for given epsilon. You see so this is just a fake free energy, right? Just to take the distribution of the M, the magnetic, the magnetization, the overall magnetization. You take the distribution, which you can solve by solving the 3 coupled ODE in a high dimensional space. Well, you solve that and you integrate out the other degree of freedom, and you call that P of M, and you take the log. This is again, this should not be considered as a free energy. But if you plot it this way, when you change E0, you see a transition, right? From when E0 is small, this is the state. This is the most probable state. When E0 crosses threshold, crosses a critical point, then you develop the 2 states here, right? And by the way, this is for a n finite n, not large number. The number of particle n is large, but not infinite. When you go to infinite n limit, this barrier goes to infinity. So there's a true transition here, right? So it's separated by an infinite barrier, the 2 states, right? Okay. This is what I'm trying to say is that if you look at in the space of m's, another variable, which is rho 1 minus rho 2, the density difference between site 1 and site 2, right? If you look at in that 2-dimensional space, then you see that it's a non-equilibrium steady state. Why do you say that? In the equilibrium steady state, because of detail balance, what it's showing here is the flux. The flux should be 0 everywhere, but this is not, right? This is not. Actually, in the disordered state, it basically the color, the background color corresponds to the density, right? Probability density. So it does form, it does center around here, but if you look around, it's basically centered around here because all the flux, all the probability flux that's going around. So this is actually very active. This is active or non-equilibrium steady state. In the ordered state, these two, if you could the quadrupole actually start to pull apart, becomes two dipole. And that corresponds to the, if you wish, symmetry breaking state. This is actually the ordered state. They are symmetric left and right. In n goes to infinity, this actually goes to infinity. So this becomes a true symmetry breaking state. And you know, in 1D, you actually cannot have, in equilibrium Ising model, in 1D, or any finite temperature, you cannot have long range order. But this is a non-equilibrium system, so you can. Two sides, yeah. No, this is a kind of, yeah. So you can solve it actually analytically, that's why. But it's still infinite in time, yeah. Anyway, yes.
So in the plot down there, if you increase the energy continuously, do you see these two poles continuously?
Yeah. So basically, this is okay. You're right. The E0 directly corresponds to energy cost, right? So the low E0 is a lower energy cost. So there's seem to form so this will happen explore very much. It's just a simulation result, right? Simulation of the full master equation. This is what you find, that they seem to form a bound state. And this we suspect the transition from here to here corresponds to some kind of delocalization of some sort. But it's hard to imagine, because that's actually equilibrium picture, right? The delocalization. But it does seem this transition from here to here happens. There's some connection being here that being broken, right? Now it become two separated. So there's an interaction between the two dipole, if you wish, that depends on the E0, and it's weakened enough that it becomes delocalized. That's that's a very hand waving thing, but you're right. I mean, it depends on E0, and at what point that you have you reach the critical point where it's flat. What does we don't notice anything special happens here, but there may be some signature there that one can look. We just didn't look. Yeah, or color field is the probability density, right? Probability density, yeah.
I was wondering if there's a way to the form like
which one? Oh, yeah. So yeah, it is. So a lot of people talk about it. This is like very similar to KL divergence, if you know what I'm talking about. Yeah, but it's So it's entropy production. So I can recommend a review article to you. So people thought a lot about that, which is I think very interesting, because basically what you want to think about is that how far is your non-equilibrium distribution away from the equilibrium distribution. And if you talk about distance between distribution, now you are in the realm of the KL diverges, Wasserstein, all that good stuff. So they can, All right, I think these are all details. If you really want to know, you can check out either the book that I recommended, or just the paper we wrote has a lot of supplemental material, so you can dive in. Okay, so what is the offshot of this? Is that now we can solve the 2D model, the two-side model exactly, especially we can solve exactly only in the, no, I lied a little bit. We can solve it numerically, the master equation of any finite n, right? That's what we showed in the result. But in the large n limit, number of particles equals infinity limit, we can use the saddle point approximation. And at that limit, we actually solve it exactly. And that's what being described here. And here's the result. Ta-da! Okay, so WA dot. 1 is the critical point, by the way. So between 0 and 1, the slope, it linearly depends on E0. The slope is actually 1. After that, it's equal to 8 times E0 Z star 1 minus Z star the 3 cube, and Z star is satisfied this equation. This is a saddle point solution. And that's the which one is it? Yeah, that's the dotted line. And AIM normalized, that's the full-scale mini-site simulation result, right? You can compute this in larger system just by simulation. And we scale it that had the same critical point and same height, and all the rest just seems to align pretty well. I mean, there's some discrepancy here, again, caused by the fact that there's a mixed state in the real simulation. And this is basically, you can also simulate the whole thing by approaching n equals to 3 with larger and larger n. And that's actually asymptotically approach this final result with a cusp. So first of all, we established there's a maximum here, and also there's a true cusp. Yeah.
Based on that, normally when I look at that cusp, phenomenon left and right slope, the power law left and right, based on that,
It's different, yeah. Yeah, this actually seems like at least the tail part has an exponential, but you're talking about this part.
Yeah, right.
This is different. Yeah, different value. We don't know why. And also, by the way, so we did this cusp. So in the full simulation of AIM model, activizing model, as well as the n two-side n goes to infinite limit analytically. Recently, people has done this calculation for actually Vic-check model. Okay, and they also see a maximum there with a cusp. So this seems to be a general phenomenon. Okay, so let me end with one chart. So why I'm doing all this? This is just a curiosity. It's pretty interesting to have a cusp. We will wonder about it, right? So why? So this is a possible explanation, a possible hypothesis is that, so, okay, so if we look along the transition line, we go back to here. Along this line, right? It all goes from disorder to order, right? With different combinations of epsilon and E0. So you can choose any point, or if you want a finite, fixed flocking velocity, this line probably just hover around here, right? Just a little bit above it. But you still have many choice of E0 and epsilon to achieve. If only thing you want to achieve is a flocking speed of, let's say, whatever speed, you have many combination of either having a very strong epsilon, a little bit weaker E0, or have a very strong E0, and a smaller epsilon. So looking at but they will have different energy costs, right? So if you look at energy cost, maybe you provide a different perspective to look at design. How do you actually design a flocking system so that it will achieve the same with less cost, right? So that was the first thought. Right, so we did that. So this is basically looking at the different combination of choice of epsilon and E0 with a constant V. V is the order parameter, the flocking speed. So if I want to achieve 0.8, I can choose any point here. The average speed would be the same, would be 0.8, okay? But why do I choose here and not here, or there, not there, right? Then if you look at energy dissipation, actually A, right, this point A, costs you the least amount of energy. And B costs you much more. So you will say, I should choose a parameter here. I'll choose my parameter E0 epsilon so that I have, cost me the least amount of energy. That seems a little too trivial, right? So what does it mean? This means that basically you want to move the lead because this epsilon part, the motion part is dominating, right? So you want to minimize this part. How do you have a small epsilon and yet still have a finite flocking speed? You by alignment being extremely strong. So that's what this A is telling you. This A is that I use alignment, strong alignment, to allow me to have a speed, a given speed, without having a too large of epsilon motion. The bad thing about it, so we also computed for each parameters combination, the susceptibility, right? So if you're flying along, some external perturbation happens, you can calculate the susceptibility, dm, dh, hb in the external field you put on the system. And that's on the y-axis. Now I may know that you might not want to choose A. Why? Because you're too stiff. Your alignment is so strong, changing of direction is very, very hard. So the y-axis is the susceptibility is actually for point A, is very low. So this could be it's a good point to think about trade-off. If you want to design your epsilon, how fast you move, the bias and E0, what's the combination to allow you to have both good speed as well as high flexibility? So I will just stop here. This is very highly speculative, but I think this energy cost allow us to think about a way that nobody else thought about before. And which is actually something, the energy cost is a very, very important part of non-encrypted system, if not the most important part of being a non-encrypted system. Okay, so let me summarize here. Some general take home. No, yeah, I'm going home tomorrow, so I can take that home with me. So a continuous energy dissipation is needed for creating and maintaining order, generally defined, in non-encrypted system. The cost directly constrains the functional performance of the system. The cost-performance trade-off relation provides a new perspective for investigating mechanism as well as design principle of the underlying system, natural or artificial. Thank you.
More questions for you?
No, I think flocking is just the initial experiment motivation to do this. But distributed computing and robotics, it's a very big deal because think about it. I mean, if in original thinking of Craig Reynolds, his motivation is to try to do animation, right? But if you turn it around, it's just doing robot. So you allow the system, the robot. So each bird is a robot instead of a computer. It's a real robot. If you prescribe the trajectory it's doing, you can do that, but you can just program it in. But wouldn't it be nicer to actually have to encode it with some kind of a sensory a system that it can sense around the environment and some decision-making capability, and just let them explore itself. So that there's a community of computer scientists actually you're using swarm computing. Actually think about the distributed computing and what kind of behavior, what kind of computing can you achieve by enabling each individual less powerful computer to do something, but collectively they do something much better, right? So I think that line of thinking is actually very, very important. They both happen in computer science, physics, local interaction, long-range order, and in biology. I'll give you one thing, something that we are thinking about very hard is about learning. So we learn to achieve some function, right? But the neural network doesn't learn with a global target function in mind. It learns by local rules, like, I don't know if you know, Hebbian learning rule, right? So how do you use some kind of local interaction, local learning, local adaptive behavior to achieve something at a much larger scale, much grander that cannot be achieved by individual? That's something I think transcend all the discipline that I talked about, computer science, biology, and in non-Euclidean physics.
For the transition between the positive and negative, why was it density dependent?
So it's a good point. That's just the model originally built. I don't think that's actually highly relevant, but they want to have a, not intensive, what is the other word? They want to have a, what? Extensive, right. So they want to filter out, they don't want a larger system to have additional advantage versus a smaller system. They want to look at the fraction. Mi, remember it's mi divided by rho of I. They want to look at the fractional. So they want to look at the fractional. Basically, I think the idea is that you only sample a finite number of your neighbor, right? So statistically, it's only the ratio that matters. If you really interact with all the people on the site, then you're right. You shouldn't divide by rho of I. But if I only sample 10 random spin on that site, then it's 10 times mi divided by rho I, right? Okay, all right.